Okay, my fault. Well, ladies and gentlemen, it's a pleasure to announce the last but certainly not least lecture we are giving this evening. You all know when we are talking about cryptography and about cryptographic strength, we have this image of n,000 computers calculating for n,000 billion years and never getting to a result. Now, what good are these numbers? Today with us is David Halton. He's been doing some research using FPGAs, free programmable grid arrays, and I hate this term. In effect, bringing down the amount of time needed to break any, or to brute force any crypto system by many figures. And how he's done this and what effects this is going to have, he's going to tell us now. Faster, owning, assured. Thank you.
Thanks a lot. So, let's see here. Title of this talk is Faster Pwning Assured. A friend of mine came up with that. You can see that's FPGA, kind of. It's the new definition for FPGAs. And I'm going to be talking about basically how to use these things, how to harness, all the gates on them to do your will and just like crack stuff a lot faster than your PC. A little background about myself. I run a small conference in San Diego in California called TourCon, and so you guys should go to that. And I also do security R&D for a small company called Pico Computing, which is a company that manufactures these cards that I'm going to be showing you today. The card that I'm doing all these demos on is actually a little compact flash card. It's this big, and it's got a Vertex 4 LX25 on it, and I'll explain that a little bit more later. First of all, how many people here have done anything with FPGAs? Just a show of hands. Oh, great. Okay. How many people have cracked crypto stuff or done any crypto stuff on FPGAs? Anybody? Okay, great. Cool. So yeah, feel free to ask me any questions about anything or provide any feedback if I'm doing something stupid or whatever. And I run this little website called opencyphers.org that I post all of my code on. All the code that I'm demonstrating today is all open source. You can download it and tweak it. It only runs on our hardware right now, but you can modify it and run it on whatever FPGA board you have. So a quick overview of what I'm going to do today. I'm going to give you a quick intro into FPGAs. It seems like a lot of you here know what they are, so I'll kind of skim over that pretty quickly. And then I'm going to go into some of the different crypto cracking stuff that I've done. I'm cracking WPA, but with modifications to cow patty. Cracking WEP, just brute forcing like 40-bit and 128-bit WEP. And I also have an implementation that cracks Landman that I actually presented on a couple years ago here at the CCC. So I'll just show you where that is today. And at the last minute, just about a week ago, I decided to work on Bluetooth pin cracking. And so I implemented a cracker that cracks Bluetooth pins if you actually capture the association. And I'm going to be demoing that with FPGA optimizations as well. And then there's a surprise release at the very end, so if you stick around, you might be able to see that. And then just follow up with some conclusions. So a quick intro into FPGAs. When you get a board like this and it has an FPGA on it, there's a lot of different things inside the FPGA. And it contains lots of general purpose logic like ANDs, ORs, XORs, flip-flop registers, block RAMs, all sorts of little components that you can connect together and have it basically function as any sort of circuit that you want. If you look inside of the chip inside of here, it actually looks like this thing on the right here, and that's a picture of the Vertex 4 LX25 die. You end up with some IOBs, which is these things along the sides and in the middle are where all of your pins, like underneath this chip, actually route into the FPGA. And so that's where all of your input comes in and your output goes out. And there's 448 of those on this particular chip. Then you have a bunch of general purpose slices, which are tiny little blocks with various different gates and things that you can connect together and configure how you like. And this one actually has close to 11,000 slices inside the FPGA there. Then there's digital clock managers, that let you take clocks coming into the FPGA and multiply them up or divide them down or adjust the phase or basically manipulate clocks. And so kind of like on your old motherboards where you set a bunch of jumpers to set like, oh, I want this to run at 300 megahertz or multiply up, my 50 megahertz clock to 400 or whatever. It's kind of the same sort of thing, but you can configure these. Then there's these block RAM little chips on there. There's 72 of them, and each one has about 18 kilobits of information that it can store. And it's kind of like a tiny little SRAM that you can just like store data in and pull data out of. So you can think of it kind of like the cache on your processor. It's extremely high speed, and it's on the FPGA, so you don't actually have to go out to other chips to pull in data or write data to them. So that's very useful. And then there's a row of DSP-48s, which are high-speed 18 by 18 multipliers and 48-bit adders. And you can configure these to do whatever sort of arithmetic you want. And there's 48 of those. And keep in mind that all these things can be doing things in parallel. So these DSP-48s can, in theory, get clocked up to about 500 megahertz. And you got 48 of them, so you can be doing 500 million times 48 18 by 18 multiplies per second if you use all of these. So it's quite a bit of speed compared to, like modern day processor. And then there's a programmable routing matrix that lets you connect all these different devices together. So if you want to connect like a slice over here to like a slice down here, or connect it to like a block RAM over here, there's this whole matrix that lets you say, yeah, I want this to connect to that or whatever. So you can do pretty much whatever you want. Now getting into WPA a little bit. This is how authentication works with WPA. And basically what I'm going to be doing is showing you that if you can capture all of the authentication handshake for WPA, you can go through and try different passphrases and figure out what the passphrase is for the network. And it's fairly simple. In this sort of diagram here, when you type in your security key or whatever your passphrase into Windows, that becomes your master key. And then it gets transformed into a pairwise master key using pbkdf2, which is kind of like a complex hashing algorithm. And then you get this PMK, which ends up being used for all of your encryption. And this pbkdf2 step is the most CPU-intensive step in the whole process. It actually ends up running about 16,000 SHA-1 HMAX, or I guess SHA-1s, but basically like about 4,000 SHA-1 HMAX. So it takes forever for it to do this one step, and so that's the step that I'm accelerating. To go in a little more depth onto how pbkdf2 works, you basically let's see here. You basically do a SHA-1 HMAC here using your passphrase and the SSID. The SSID is used kind of like the salt. And then you run through 4,000 times and do SHA-1 HMAX and just like take the output and stick it into the next SHA-1 HMAC. And so this step takes forever. And that just generates the first 20 bytes of your PMK. And so then you have to run this again to generate the next 12 bytes down here. So you actually have to do this twice, so it ends up requiring like 8192 SHA-1 HMAX in order to generate your PMK. Now, if you look at the SHA-1 HMAX, basically an HMAC is taking whatever algorithm, in this case SHA-1, and taking your first key and XORing it with 36 all the way across, and then also SHA-1ing like this T value, which is whatever you're HMACing. And then over here, you basically SHA-1 the master key XORed with 5C, and then SHA-1 the result of this. So essentially, you're kind of, for this initial one right here, you're doing a SHA-1 update with this value, and then a SHA-1 update with whatever your SHA-1 HMACing, and then doing a finalize and taking that and plugging it into down here. And why I show you this is because these two values right here can actually be cached because they're going to be the same result every single time, so you don't actually have to do those SHA-1s every time. You can cache the output of those, and then the only SHA-1s you have to do is this one and that one. So it requires a lot less work when you're doing SHA-1 HMAC, especially many times in this case. So after you run through this whole step, then you can basically compare it with all the network traffic you have to see if it's the right passphrase or not. My particular FPGA implementation uses 8 different SHA-1 cores, and it uses block RAM to buffer all the values. And I'll show you kind of how this works in a minute. But it uses kind of a ring buffer, so as long as you can keep the buffer full, it'll actually fully utilize all the SHA-1s. And this is somewhat how it works. I got this huge ring buffer, and it just starts filling up the top of it, all the way down to the bottom. So now all these have values that it wants it to run the SHA-1 HMAC, or the PBKDF2 on. And then once it gets down here, then you initiate the whole thing, and it starts taking like the first 8 up here, feeds them over to the SHA-1s, those generate the values and sticks them back in here. And then it goes on to the next 8. And while it's working on these, then it fills up the other end of the buffer. So as long as you're filling these up, if there's any hiccups, then it still has all these full, so it can go through those smoothly and keep the pipeline full and stuff. So that's basically how that works. The result of the FPGA optimizations is if you run CowPatty on a normal PC, you get about like maybe 25 to 70 per second, depending on how fast your machine is. Using AirCrack, they have some MMX optimizations that run at like 100 per second roughly. With this little compact flash card, you get about 430 per second. So that's maybe like 6 times faster or so than a fast PC. And we also sell these in clusters, so if you have 15 of them, you can get like 6,500 per second and so on. Another cool thing is that we decided that we should generate some hash tables because lots of people use the SSID of Linksys or default or whatever, and so a lot of people are going to have the same salt. So why don't we just generate, a huge dictionary for those individual SSIDs? And so once we run across those, all the work is done, and we just run through all of our pre-generated values, and then we can crack it a lot faster. So this guy that I know, RenderMan, sent me this word list that has 1 million different commonly used passphrases in it, and also the top 1,000 SSIDs. And so he wanted me to generate all these pre-computed values. And this is kind of funny. The word list that he had was actually acquired through Google hacking and stuff he got from like Kevin Mitnick and some interesting sort of sources. So he tried doing this himself, and it took him 1 month to compute all this stuff on his lab of workstations, his cluster. And after computing for a month, he found out that his word list had return characters at the end of every line. It was in MS-DOS format. And so most people don't have return characters at the end of their passphrases, so it was all work for nothing. So I did it on one of our clusters with 15 cards, and it took 2 days, so 15 times faster than his cluster. And these tables are actually, they're getting posted right now. I'm not sure if they're up on the internet yet, but there's going to be torrents out for them if you want to grab them. And then you can use CowPatty and crack people's access points if they're in the SSID list. So I'll give you a quick demo of this just so you can kind of see how CowPatty works. So CowPatty, there's all the source and stuff. I guess you can kind of see that. But this CowPatty application lets you just, if you have a capture, a dump of the authentication, then you can feed it this info, and it'll go ahead and crack all the stuff for you. There's also this GenPMK application that generates the pre-MK dictionaries. So you can use that. I generated some shell scripts here to make this a little bit faster. I'm going to start up CowPatty without the FPGA. And so here's a dictionary file, there's a dump, and there's a SSID, which is something clever. So I fired up a screen session. Right now, it's done like 100, 200, 300 passphrases there, so you can kind of get an idea. Right now, this is maybe running at about 50 per second, and I don't think I'll let this continue because it's so slow. So, oops. So now I'm going to run it with the FPGA. This script right here swaps the image on the FPGA, so it's running my cow patty image. So now it has totally new hardware on it, and it's geared towards cracking PBKDF2. So this should run on the FPGA. So right now it's running on the FPGA, and it's doing about 430 per second. And it should find it in a couple more seconds here. So you can see that it's noticeably faster. Yeah, there we go. So it found the passphrase right there. Now, okay, on to cracking WEP. A friend of mine wrote these tools called Airbase or JC WEP Crack. Has anybody ever used that or heard of it? No? A couple people. Okay, cool. Yeah, it's one of the other implementations of AirCrack. Like there's 24 of them now or something like that. And it's pretty cool. He wrote it all like object-oriented in C++, and so it's kind of slow, but it works really well. And there's a bunch of different tools that he has in there. I'm not going to go over it too much, but cool things like he's got an application that'll strip the Prism headers and like interchange them to whatever Prism format you want, since everybody has their own. He has like the replay attack and other things like that. And JC AirCrack, AeroDump, all these kind of standard programs. It's basically a whole suite of web cracking tools. This is kind of what JC AirCrack looks like. So you can choose what statistical attacks you want to use and all that kind of stuff. But what we're going to be focusing on is JC WEP Crack, which is just a brute force web cracker. And it actually runs on OS X and Linux and stuff. And it's all client-server based, and so you can have a distributed set of a bunch of machines working on different areas of the key space. And it'll send out jobs to all of them, and it's pretty cool if you have lots of machines. So this is what the server looks like. And this handles sending out the jobs to all of your slave machines. And so you can have a bunch of these clients hooked up, and it just all works. Or you can have one of the clients hooked up with an FPGA. And let's see. This is kind of a future model where he wants to integrate into JC AirCrack. So basically anything that does like RC4 cracking or web cracking, you can just use his API and it'll automatically offload it to the FPGA. And he also wants to build in support for other sorts of devices, so it can just be kind of abstracted to the point where you can have different things accelerate it, and it just works without even knowing it. So yeah, I'll just skim through this. Okay, has anybody here cracked WEP before? Yeah. Okay, cool. Everybody understands how WEP cracking works, kind of, sort of. Okay, well, for brute forcing WEP, basically, you sniff some sort of packet, and then you determine the PRGA output of RC4. How you do that is the first few bytes of every packet is predictable, the plain text, and so you take that predictable plain text and XOR it with the packet that you got, and then you get the actual output from RC4 for that particular key in IV. And so how you verify if you have an actual key is you run through RC4 with a particular key and the IV that was transmitted in the packet, and then you look at the output of RC4, and if that matches what you get in the packet, then that's pretty close. Like it means that it's probably the key, but you probably want to try with some other packets just to make sure, just in case there's two keys with the same IV or the same PRGA. So then, like after you do some checking, if it looks like it's the right key, then there you go, you just found it. So it basically just involves running a bunch of RC4s until you find the right key. With my FPGA implementation, I usually use this one that uses 32 RC4 cores. So there's 32 RC4s running in parallel on the FPGA. And it uses block RAM for S boxes because S boxes take up a lot of space. And it'll try every key between start and end. So you can give different ones start and ends in different areas of the key space and basically split it up to however many times you want. Looking at RC4, if you're familiar with it all, there's this initialization step where it initializes the S box, which is a permutation. So like S0 equals 0, S1 equals 1, S2 equals 2, and so on. And then in the KSA, it basically does a bunch of swap operations based on the key. So it just starts swapping around values because it's permutation. And depending on the key, you know, the output of that will be a certain permutation of 256, like in there. And then it uses that permutation to basically output bytes and do more swapping for the actual PRGA output. Now, when you look at this from an FPGA perspective, this initialization is going to take at least 256 clock cycles when you're using block RAM, because every clock cycle you're writing in a new value to initialize the block RAM. And so that takes a lot of time right there. With this, that would also take, you know, at least 256 clock cycles with optimizations and stuff. And so just the initialization is taking up a lot of time. So, oh yeah, and basically that's the input and that's the output to the whole thing. But I'll go into kind of how I optimize that a little later. Right now, with the card, all you have to do is tell it, like, you know, start at this key, end at this key, and look for whatever PRGA you have. Oh, yeah, babe. Okay, there we go. So like, let's say key 0, key 1, key 2. Key 0 is dude, beef, dead. None of those match the PRGA. And so then we tried the other keys. And then it turns out that, oh, look, this one is the matching key. And so then it turns out that, yeah, that's the right one. So now we know what key it is. Yeah, for optimizing the initialization here, my original thought to do this was to have two block RAMs that kind of swap between each other for each RC4 core. And so initially, to initialize this block RAM, we initialize that to 0 through 255. And then RC4 uses that one, and at the same time, I'm kind of filling up this other one, and then it just swaps back and forth between them. And so the initialization is done in parallel. And I kind of came up with a better optimization for speeding that up. And how that is during RC4, in the KSA step, it actually writes to every value inside the S box, because when it's doing the swap, it swaps like every value out. And so my idea was that with all those writes, we use a 16-bit block RAM instead of an 8-bit one. And during each 16-bit write, we write into like the top 8 bits with whatever the address is that we're writing to. And so at the very end, we end up with, you know, like all the values we're actually using in the bottom 8 bits, and then all the initialized values in the top 8 bits, and then just swap in between using the top and the bottom, sort of. So it requires less block RAM, basically. So yeah, at the very end, you end up with something kind of like this, and then you just use this for the next one, and then swap back over to that one. If that makes sense. So yeah, so then you start initializing this one while you're using the top half for the next one. Does that make sense, kind of? Yeah? Sort of. Okay. So my next demo is going to be JC Web Crack using the FPGA and with matrix effects. Everybody down with that? Yeah? Okay, so with this, I built another handy-dandy script. This will swap me over to the RC4 cracking image on FPGA. So with this, you just give it a PCAP file. It'll grab one of the packets out of it. And then you tell it how big the WEP key is. In this case, it's 40. And so right now, it's starting up the JC Web Crack server, which is running locally. And you can see it's checking out chunks right now to things in it, or there's key sessions here. There we go. So there's some matrix effects. Since this isn't taking up any CPU power on my machine, I use it for, you know, doing cool graphics and stuff. This will take a little while to finish. The key should be like 0011223344. But you can see that this one has 0 through 0040 and a bunch of zeros. And this one has 0040 to, so the chunks are, I think they're like 20, was that 24 bits or 20, yeah, a certain amount of bits. Do you guys want to wait to see this finish? It has some cool graphics at the end. Okay, we can wait for a minute, I guess. Does anybody have any questions while we're waiting? No? Okay. Oh, yeah. I use all of like the Xilinx tools. They have tools you can download from their website called, use ISC Project Navigator, which is like their main kind of tool. Use like Model Sim and chip scope and all the standard Xilinx stuff. Okay, it's getting closer here.
What's the price of one of those cards?
These compact flash ones that we sell are like $2,500. So they're kind of pricey. You can get dev boards a lot cheaper if you want. Oh, there we go. Yeah, so cool. So I found it. Woo! Okay. Yeah. So on a fairly decent P4, you can get maybe about 300,000 per second. If you anybody have any numbers on how many RC4s you can do per second in your computer? Okay. Well, on my laptop, my fast one, I get about 300,000 per second. On this little compact flash card, I get about 9 million. So that's was that 30 times faster? Yeah. Yeah, so 30 times faster on this little compact flash card versus my laptop. And if you have a cluster, you can make it faster if you want. So definitely a speed improvement there. Now, moving on to Landman. Last time I presented, I was just starting off on working on this, and now it works a lot better. But basically, I have this thing that just cracks landman hashes. If you don't know what landman is, it's what Windows uses for doing all of your password authentication. So if you can get the landman hash off the network or off your registry or whatever, then you can run it through this and it'll crack it. And basically how it works is you send the hash over to the FPGA. In this case, I can crack 128 hashes in parallel. And then it generates a bunch of passphrases. So, it starts with like, is your password A, is it B, is it C, and then on to like, up to, I think 7 characters long as the max one. And then it generates these hashes and runs a crypt on them, sees if it matches your hash or whatever, and if it does, then it sends the password back and says, hey, we cracked this. How this works is a little complicated. I basically have like a variable radix counter, so you can say I just want to crack A through Z or A through Z and 0 through 9, or I want to crack like all the typable key space. And so it basically counts through like 0 through 26 or 0 through 36 or whatever, and then it converts that over to an actual password, and that gets fed over to the modified DES crypt function to run landman on it. And then it saves it out into a ROM. Well, it saves out the password that corresponds to the actual generated password into the ROM, and then it puts the hash into a pipeline. And this pipeline is pretty huge. I think it's 128 registers. They're all 64-bit registers. And then kind of how it works is it does a compare on each one of these to each one of our hashes that we're cracking, since we're doing 128 in parallel. And then if any of those match, it figures out which one was cracked, pulls out the right password, and then saves it into like our output ROM, which you can read back from the PC. So it's a little complicated, but when you're doing 128 64-bit compares in parallel, it's kind of hard to fit on the FPGA, so that's why I use the pipeline so it can spread it out along the FPGA. And then it says, okay, well, I cracked this one, and so it sets the status bits, so you know which ones have been cracked and which ones are still working. So this one actually has a graphical interface, and it runs on Windows, Linux. It should be easy to run on OS X because it uses WX widgets. And there's also a fast mode. If you're just cracking a single hash, you can take away all the space that it uses for the 128 compares and just put on 2 extra DES cores, so it does it 3 times faster. And automatically loads the required FPGA image and supports multiple cards. So if you got a couple hundred cards in a system, it'll split it up and do it really fast. Some results here on a PC. I get maybe about 2 million per second. On on this card, we're getting about 125 million, and in the fast mode, it's about 375 million. And that'll probably, well, this will probably vary depending on your PC. And with this one, if you have a bigger FPGA or smaller FPGA, it'll vary a little bit. But there's some stats on how long it takes. So it's quite a bit faster. I'll do a quick demo here. Let's see. There you go. So let's do, all these are A3Z, so I'm just doing the fast one so you can see it work really quickly. So this is, I think, 1,000 hashes that it's cracking in parallel right now. Or, well, not entirely in parallel, but it's already found like 76 of the 1,500 hashes. And you can kind of see that how landmine works is it actually splits up your up to 14 character passphrase into two halves. And so this cracks each half independently. So this one, it's only found the last half. But with these small ones, it finds them pretty quickly. But yeah, this one it found the half there. And so it's doing it quite a bit faster. If you think of like actually how many compares it's doing, it's about 6.4 billion compares per second. Those are all 64-bit compares. And I guess, wait, the 50, that's the wrong number, but it's probably even more than that. I don't know. So that's that. You guys have any questions about the landman cracking stuff? Anyway, okay. So I'll close that. No, this new thing that I threw together, Bluetooth pin cracking. A lot of people here use Bluetooth. Yeah, of course, hackers. So first off, this attack does require really expensive hardware to do. You need to have a protocol analyzer that I think costs about $10,000. So you can either try and hack your own together or buy one, but it's a little expensive to do. Basically, how this works is you use the protocol analyzer to capture the authentication, just like you do with WPA. And then you just try a pin. If all the values match up, then that's the right pin. If they don't, then it's the wrong one. And it just goes through and does all those. This attack was originally explained by, I won't even try to pronounce those names. But I guess the Theory Zoller, is he here? Anybody? No? Okay, well, he's giving a talk tomorrow on Bluetooth pin cracking and Bluetooth hacks and stuff. And so he supposedly demonstrated this at hack.lu. And this is basically the same sort of thing that he did, but with FPGA acceleration. And all this is based off of Safer Plus. So if you capture the whole authentication for two Bluetooth devices, basically the master first sends across this 256-bit random number, and then the master also kind of generates its own random link key and runs it through an algorithm, and then sends across like an encrypted version of that. And then basically all this is kind of like a key negotiation. So after this section, both sides have the same link key, so they can actually encrypt data and send it across. After they have this link key, then they send across a random number, and this one will send across a random number. Then the other side just encrypts it with what it thinks the link key is, sends back a hash, and if that matches, then it sends back across its own random number, and the other one verifies that it has the right link key. So this is just creating the link key, and this is verifying that both sides have the right one. And so that's how the authentication works. And after the authentication, both sides know that both sides have the right pin, and they also have link keys so they can do all of their Bluetooth communication encrypted from that point on. And both sides will actually keep those link keys stored on the device, and so you don't have to keep on repairing. Like when you connect your cell phone to your laptop, you only really type in the pin once, and then it kind of remembers the pairing after that. So if you can capture this authentication, then it's a pretty small key space for just 4 digits, and so that's pretty fast in general. On a PC, I think that people have been able to do it in about a fourth of a second. And for like, 6 to 8 digits, it'll take a little bit longer, but still it's pretty quick because it's such a small key space. My implementation is a command line app that does kind of the same thing as Thierry Zoller's. And it required implementing this E21, E22, and E1 algorithms. And it actually only has one implementation of Safer. That's a 16-stage pipeline. And each one of these algorithms uses Safer in some way, and all sequentially. And so it actually runs Safer plus about 7 times, I believe. And this is basically what it does. It runs this E22 algorithm to generate kind of like an initial key. And then, well, this is how you crack it. So then you get one of these values that's actually sent across the network. And these are encrypted by XORing them with this K in it. And so you decrypt those, run them through E21, which kind of generates the link key for both sides. And then when you XOR those two together, you get the actual link key for the whole conversation. And then down here for generating these hashes to verify that the authentication is correct, then you just run these with the link key, with the random number that's sent across, and with the MAC address of the device that's sending it. And then basically if those hashes match up, then that's the right pin. If they don't, then it's the wrong one. So it just goes through every pin and tries every one until they match up. So, oh yeah, and all these red values here are values that we actually capture off the air, and this is what we're cracking. So you need to have all these different values in order to actually, crack the pin. And it's just the pin that's unknown in this whole thing. So how this whole implementation works is I have a pin generator that just generates, like pins starting from 0 all the way up to, like a 16-digit pin. And it generates the first 16 and starts sending them to Safer on each clock cycle. And because this is all pipelined, it'll take 16 clock cycles for it to fill the pipeline and actually get data coming out the other end. So you send in the first pin, and then 16 clock cycles later, you'll get the output for that pin, and then the next clock cycle, you get the output for the next pin, and so on. And so after 16 clock cycles, it actually takes the output of that and kills this whole thing here, and feeds the output back into Safer Plus because it needs to do the next E21. And so, after the 16 clock cycles, when we get the first output, it loops it back in for the input and runs the next Safer on the data. And then it basically keeps on doing this, so then it runs it through E1 by doing the same loopback thing, and the next E1, and all that. But basically, it only needs one Safer Plus in order to do the whole thing, but it loops it through 7 times in order for it to actually crack, or do 16 different pins. So after it's gone through and looped all of that, and it's gone through the last E1, then the first output value that comes out of that gets compared with the SRES values that we have. And if those match up, then it stops the whole thing and says, okay, we found the right, the right pin here. So pull it back, verify that it's right, and report it to the user. If it doesn't find anything, then the pin generator just keeps on going and filling it up again, and the whole process repeats for the next 16 pins that it generates. And all this is going at about like 100 million per second, like 100 megahertz. So if you think of how many pins it can do per second, it's basically about, like 100 million divided by 7, because it has to run through 7 times. So, yeah, one thing that's kind of cool is that because it stops it whenever it finds the correct pin, then all we have to do is read back what the last pin was that it generated, and then subtract 16 from it, and then you know what pin actually caused it to stop. And so that's another logic optimization there. But some results on a P4 using BT pin crack or BT crack, you're able to get about 40,000 pins per second. And with my FPGA implementation, on the low end, you're getting about 10 million per second. And if you run it at 100 megahertz, then that's like more like maybe 13 or 14 million per second. So pretty quick compared to that. It's about 250 times faster. And I'll show you it working right now. So let's see here. I've got these capture files that you can look at if you want. This is from one of the protocol analyzers. It's just a dump. So yeah, there's the in-rand value that it transfers across. Oh yeah, there's the COM keys. So this one is coming from the master, I think. And then, oh yeah, it's retransmitting it a bunch of times. Yeah, for some reason it does that. And then, oh yeah, there's the authentication RAND values and so on. So if you can capture these and you just take these values and then you have everything that you need. At the very end of this, you'll see the SRAND values. Where is that? ERAND, oh yeah, SRES. There we go. Yeah, I don't know if you can see that, but there's like the 4 bytes up there for SRES and 4 bytes down there for SRES. And so those are actual hashes that we verify with. So I've got some scripts here to do this. But basically, you just run BT pin crack. You tell it to use import feature, and then tell it to import the values from that file, and then you give it the MAC addresses of the 2 sides that are doing the communication. So I'll just run this script here. So right now it's running on my PC, and this is a 6-digit pin, I think, that's cracking. So going at about 40,000 per second. I should find it pretty soon, I think. Yeah, there we go. So I just found it. It took, was that about, was that 17 plus 1, 18 seconds for the whole thing. And after I got this to work, I tried running this on the FPGA, and it cracks this one so fast that I decided, hey, I'll just run on all the capture files, because then I can actually measure how fast it runs. So this is cracking 6 different capture files. Notice how fast it cracks the first one. Oh, oops. I gotta swap. There we go. Yeah, so just cracked the first one, instantaneous. It's working on the second one, which is like 7 or 8 digits, I think. Is that 8 digits? That's 6 one. Yeah, there. So it just cracked 6 different pins, ranging from like 5 digits to 8 or 9 digits. And it did it in maybe about 5 seconds right there. So yeah, that one was 9 digits right there, or 8 digits, yeah. So yeah, pretty cool. So the surprise release is that my friend Jake Applebaum and Ralph were doing a talk tomorrow on FileVault, and I was talking to them last night, and it turns out that FileVault actually uses pbkdf2, the same function that WPA uses for the hashing. And so it turned out that I could do some small modifications to my WPA stuff and make it work for FileVault. So I threw that together last night and actually got it working about an hour ago. And so I'm going to be demoing it tomorrow, unless you guys want to see a demo today. I can demo it right now if you want. Yeah? All right, just for information's sake, oops. The talk tomorrow is in Sol 1 at 11:30 a.m. So if you can get up that early, you should check it out. I'm not going to explain how this works too much, just, but I'll demo this also after they explain it. So let's see here. Let's swap over to it right now. So I modified their code to do passphrase cracking, and you just feed a dictionary file and the DMG file for FileVault. So I've got this dict file. It's the same one for the WPA stuff, kind of same sort of stuff. So feed a dictionary file and the DMG, which is test.dmg there. And so it's running through with pbkdf2 on it. It runs about 4 times faster because it only does 1,000 iterations instead of 4096. So This is just running on my PC, and it's a little bit faster, as you can see. It should find it pretty soon. There we go. So I found the passphrase, which is 1, 2, 3, 4, 5, 6. And so then you just feed it with the same arguments, but you also give it the FPGA number, which is 0 because I only have 1 in here. And this should run it on the FPGA. So right now it's doing about 2,000 per second, and it found it in a couple seconds there. All right, well, if you want to see how that whole thing works, check out their talk tomorrow. And some conclusions here: get an FPGA and start cracking. You know, download some of my code, try running it, make your own code, whatever. Add cool matrix ASCII effects when you can, because you aren't trying to, you know, just like squeeze that extra, you know, like assembly code out of your optimizations. And I don't know, you can waste tons of CPU cycles doing cool stuff instead of cracking passwords now. And choose bad passwords, please. That's always a good thing to do. So that's our card. It actually, the reason why it's so expensive is it has a bunch of other stuff on it. If you want to look at this later, come up here and I'll show you. But it has tons of other stuff on it. It's got 64 megs of flash, 128 megs of RAM, gigabit Ethernet. You can get it with a PowerPC on it if you want. And you can run Linux on it and stuff like that. We sell them in clusters of 15, so if you take the $2,500 and multiply it by 15, that's about how much this thing costs, which is pretty pricey. We're also working on Express Card that'll run in your MacBook Pro. And I've got PCBs here. We're still working on getting all the software working on it right now, but this is kind of like our crypto cracking card of the future, which will probably be out in a few months. And it has a lot less stuff on it, so it's easier for us to manufacture. We're going to price it maybe around $1,000 or so. And it should be about 3 times faster than our compact flash one, because it uses the newer chips and stuff. But expect to see this come out in a few months if you're interested in buying some stuff. And some thanks, Johnny Cash for doing Airbase, Josh Wright for writing CowPatty, RenderMan for getting me to generate some hash tables, Beetle, who found out how to do this on OS X pretty easily, and Jake Applebaum and Ralph Weinman, and the audience here. You're pretty cool. So here's all my info. If you have any questions, feel free to ask them. Any questions? Yeah, back there.
All right. Have you considered applying this FPGA cracking to any other crypto algorithms than the WPA and the landman hashes and the demos you showed? I'm sorry if you covered that already. I missed the beginning of your talk.
Yeah, actually, that's a good question for people here. The tough thing is that a lot of stuff out there is kind of made so even if you can crack it like 1,000 times faster, you still can't really crack it. Like 128-bit or even 256-bit is still pretty impossible. So there's a lot of stuff out there that's kind of too tough, and so I'm just kind of looking for the low-hanging fruit of crypto stuff. And even when you think about it, like FileVault and CowPatty, it only does like maybe a few hundred or a few thousand per second, and so that's like way too slow to even think of doing a brute force attack on it. So it's mostly just kind of trying different passwords and seeing if they work. If you guys have any ideas on like the kind of the low-hanging fruit, where if I could do this 100 times faster or 1,000 times faster, then I could totally break this. Please let me know, because I'm trying to find those. One thing that I have been thinking about is it turns out that WinZip also uses the PBKDF2 stuff. So and I think it actually uses 1,000 iterations. So probably this stuff could be easily used on WinZip also. That's a question for you guys. Do you have any ideas of things that I could use this for? Or anybody? Or do you know of anything?
No, sorry. I just have a friend of mine who does some research on RSA.
Oh, okay.
Well, yeah.
Oh, yeah. I kind of mentioned I'd talk about some RSA stuff, but
okay.
Yeah, I don't really have anything prepared. I kind of threw in this other stuff instead. So
yeah. Thanks anyway.
Yeah, thanks. Any other questions or comments? Anything that should be cracked? Yeah.
What's the I/O bandwidth between the FPGA and your computer?
What's that?
The I/O bandwidth between FPGA and your computer.
The I/O bandwidth. Compact flash is extremely slow. This card maybe tops out at a couple megabytes per second, just because of the bus. So it's only really useful for applications where you're just sending a little bit of data and then it's doing tons of computation on the card and just spits back a little bit of data. Yeah, so with our card bus card that we also sell, that'll top out at about a theoretical gigabit per second, but in reality it's maybe about half that. With our Express card, that'll top out at about 2.5 gigabits per second full duplex, and so maybe you're going to get half that or a little over half that, but the Express card is definitely a better solution for applications where you're sending lots of data back across the bus.
Yeah, that sounds pretty fast. A couple of years ago, there was a talk here about a possible kernel accelerator device. Have you heard of it? They tried to implement crypto and so on FPGAs and provide these services via Linux kernel modules. So what I would be interested in is how many times can you reprogram these FPGAs, since it might be necessary to reconfigure them once in a second or maybe once a minute or something.
Yeah. That's kind of interesting that you brought that up, because our compact flash one, actually it has a flash ROM on there that we use to load the FPGA from. And so you have to upload your image to the flash and then tell it, okay, load this particular image off the flash on the FPGA. And so that takes some time just because the flash is really slow and you have to program it first. With our Express card, we actually designed it so it has an external Express card PHY on it. So when you plug it in, it recognizes it and stuff like that, but it doesn't actually have anything on the FPGA. And you can use the extra chip on there to program it directly from your PC. So you don't have to upload anything first. You just stream the file directly onto it. And so it's a lot faster. You can program it like almost instantaneously. I think that with this one, it's like a few milliseconds to program, and with this would be like in the microsecond sort of range. So so we're really designing this so you have to plug it into a PC. You can't run it standalone like this one, and make it so it's really quick to swap out images, rebuild them, and change them out whenever you want. And you could also do like partial reconfiguration if you just want to change one particular algorithm on there, or change resources and stuff. So this one's kind of like our future sort of idea for crypto cracking stuff. Any other questions? Oh, go ahead.
Just a second.
I was just wondering, do you need export licenses for these devices in the US these days, or?
I don't think so. The FPGAs themselves are mostly manufactured in like other countries, and the actual code is all open source, so it kind of falls under the open source export licenses, I guess.
Yeah, right, but no, I'm asking about the hardware.
The hardware? I don't think so. I think we're still working on trying to get a distributor in Europe, but I mean, if you want to buy one, we can just mail it to you or something. I don't know. I guess we haven't had anybody come up to us about that. So. Back there? Me? Oh, sorry.
Well,
I guess, yeah, why don't you go ahead first.
Your competition has implementations of FPGAs hooked up to hypertransport systems. Do you have anything planned in that regard? You have a dual socket Opteron. You have an Opteron plugged into one socket, and the other one is the FPGA, so you have a very high bandwidth.
Yeah, like the DRC chips. Yeah, there's this company called DRC that makes an FPGA that plugs into an Opteron socket. And so if you have, so it basically uses hypertransport for the bus, and it's a lot faster. We don't have anything that does that. We were just kind of, our whole idea on that is that, like with the limitations on how fast like RAM can transfer and stuff like that, it just seemed like it would be a better option to go to PCI Express, because we're building backplanes so you can plug like 8 of these into a backplane and use 8x PCI Express, and it seems like it'd be fast enough for our purposes. But yeah, for I guess extremely high speed stuff, it seems like you get to a certain point where you can't transfer it off of your like 1,000 hard drive RAID array fast enough, or transfer it onto it, and I don't know, it seems like there's kind of a top of the line where, you know, you can't, where your bus doesn't really matter in certain applications. So do you have any applications where you could use, you know, like tens of gigabits per second?
Well, we're actually looking into structured Gauss over finite fields.
Oh, okay.
Basically doing a couple ideas. So there's nothing concrete yet, but attacking AES or at least the toy examples initially, and then
Okay.
seeing how far we get. And it's there's several attempts either over F5, so it's a border base, it's a gradient-based computation, or alternatively trying to do it with border bases, but. And then just, I mean, any kind of linear system solving over finite fields.
Oh, okay. But so you require a lot of data for that, or?
Yeah, I mean, having 10 or 20 gigs of total data at the very end is not that unusual. I mean, certainly 32 or 256 megabytes is not going to cut it.
Yeah. Oh, yeah. So you're talking about like for your tables and stuff like that, you need to be able to save it off and pull it in and stuff.
Well, the systems have a tendency to get quite large. They are usually over F2 or F2P. So, I mean, it's all at an experimental stage. We're doing work for an unnamed ugly big oil company, and we have some resource money to buy funny stuff and try to explain to them why we need that for their particular research purpose. But we are doing crypto research on the side. And
I guess if it's really important that they need to communicate with each other fast, then you might want to go with the DRC or I guess like Cray has their own FPGA stuff in the XD1 that uses a higher speed backplane or something. But yeah, we're kind of aiming more towards something that you can plug into your laptop, and then if you want to, you know, do all your development on your laptop and then take them out, plug them into your server, and have a bunch of them there, and just make it really scalable like that instead of the really high-end sort of academic stuff. Any other questions?
It's just for an information. We have ordered some FPGA 4 from Vertex, and we need an agreement, an export agreement, because the US government don't want some people use this FPGA for make nuclear bomb or massive destruction weapon. So we need an agreement.
Oh, interesting. What is the law like for that? Or can you explain that more?
Excuse me, I don't understand exactly.
Oh, I guess we can. I'd be interested in what the laws are like for that. Maybe we can talk about it later, offsite.
Yeah.
Okay. Yeah, go ahead.
Did you know any open source software for using and emulating HDL code before sending into FPGA or CPLD, or did we have to use proprietary software before using any FPGA?
That's a good question. There's an open source simulator called Icarus that you can use for, you just write your Verilog and then you can simulate it, and it'll run as if it was on an FPGA. But Xilinx is the only company that has something that'll actually, build the files that you can load on the FPGA, since it's all proprietary. But I know a lot of people that do all their stuff in Icarus, and then when they actually go to use it on the FPGA, then they run it through the tools. And all their tools are pretty much free. You can download trial versions from their website. They have a Linux version that only runs on Red Hat Enterprise, but it's based on command line tools, so you can script it all to build your stuff. And so it's not too bad. Go ahead.
Do you have any experience with some advanced synthesis tool like Synopsys? Not Synopsys, Simplify?
Oh, Simplify?
Yeah,
a little bit.
Instead of the ISC?
Yeah, I've used it a little bit, but I kind of prefer to use IC stuff just because people that are downloading this off the website and building it don't really want to spend $20,000 on Simplify to build it. And so if I make all my code so it only runs on Simplify, then it kind of reduces our amount of people that can use our stuff. But we have used it for some of our kind of higher end designs that are proprietary. But I kind of prefer the Xilinx stuff personally. So any other questions? All right. If you have any other questions, feel free to come up and ask me. I'll have these cards laying up here, but thanks a lot for your time. I'll talk to you later.